Alright guys, so in the intro video we talked about several of the projects that we're going to be working on for the next few months, some of these projects even probably the next few years. One of those was nanocrystalline materials. So we didn't really go into much detail on it, and all you saw was this picture of this little itty bitsy piece of like coppery looking material, and in fact that was copper. It's a copper tantalum material, and it's a nanocrystalline. So what nanocrystalline basically means is if you have like a metal alloy, and that metal alloy, like let's say this is just a piece of copper, you buy it from the foundry, and when they take that molten copper, they pour it into a mold, and then they let it cool down slowly. What will happen is inside this piece of copper, if we were to zoom into this, what you're going to see is that there's all these things in there called grain boundaries. They'll look something like this. And these grain boundaries, if we zoom into these really, really far, we get like a good electron microscope, what you're going to see in these grain boundaries is copper atoms that are perfectly lined up. Well, not perfect, but for all intents and purposes, they basically are. And that's in 3 dimensions. And so these things have this, that's why it's a crystal. And so we always try and manipulate these grains to try and make metals have different properties than, to improve them in different ways for engineering. So like if we were to take this piece of copper and if we were to do an anneal on it, which is where we put heat on this thing. So we put a blowtorch on this piece of copper. What will happen is some of these grain boundaries will begin to grow into each other. And so the grains will become larger. And so when you have larger grains, it becomes more malleable. It's easier to bend and that kind of thing. And if that's the property you're going for, that's great. But if you want strength, what you want is, you want the opposite. You want these grain boundaries to be really super small. And you want to get them as small as possible. Now the reason for this is, when you have grains on the outside of them, a good way to think of it is they're basically really sticky on the outside edges of them. And so that means that outer surface has a lot of stickiness to it. So if you could take, let's say, one large grain that's like this. So this is our grain. Well, if we had this grain and let's say we split it in 2. Okay, so that has good stickiness between these 2 surfaces. So then what if we take it and we were to split it again? Well, now we have that much more surface area. That means we have that much more stickiness. Then what if we split this in again? And then what if we do it here and here? And every time we do this, we're getting more and more of that surface area. So this is called the Hall-Petch effect. And so basically what that does is, if we can get the crystals where they're really super small, then because the surface area becomes so large in that same area, they stick together really, really solid. So you can take something like copper, an alloy that's 90% copper, and you can make it stronger than steel, if you can get the crystal size small enough. It's extraordinary. It's amazing how strong it is. One of the problems with nanocrystalline materials is that it's so hard. It has such good strength to it that when we go to test it, we keep breaking the testing rig. That's a wonderful problem to have. So we've tried out different ways of testing it. So like one of the ways how we tested is what's called compression testing. So using essentially the same device but without the furnace, and we have 2 pistons, one on the top, one on the bottom here, and we have our nanocrystalline sample in between these 2. And these 2 pistons push down. Now, on the intro video, if you watch it, if you hadn't watched it, I suggest you go and check it out. There'll be a link put to that right here. But if you had seen it, you would have seen that little tiny piece of copper in those 2 round things. If you look closely, what you're going to see is that these 2 round things, which are made out of steel, were actually gouged out by that tiny piece of copper. So this 90% copper metal alloy, because of its nanocrystalline nature, was now significantly stronger than these steel platings. To what level we didn't know. So then we took it to the next level. So we replaced these steel platings with we replaced them with tungsten carbide. For those of you that don't know what tungsten carbide is, that's what a lot of our machining tools are made out of. For when we got to deal with like the really big stuff, if we got to cut stainless steel, or if we got to cut Inconel, or these really exotic super alloys. And so it's tough stuff. It's super tough. And so we use these tungsten carbide elements on here, and they broke. they actually shattered. It was unbelievable. And once again, the top copper tantalum came out of there just fine. 90% copper against tungsten carbide lost. So that's basically it. So we're going to show more stuff on that. This is just kind of a real quick tutorial just to give you guys an idea for what it is, what nanocrystal materials are, why they're important. So they're super strong. We're not going to be doing too much with the copper tantalum because the rig that we set up is for doing lighter alloys. So we're going to be doing magnesium lithium alloys. We've only made one sample so far. We're very happy with it. It was stable, so that's good. It didn't spontaneously combust or anything, so that's always nice. And we're going to continue that work, and so you're going to be seeing more of that. So the next video we do on this, we're going to end up having, you guys will be able to see the equipment, how it's processed, and how it's made. So this equipment hasn't been used in a couple of years, so it's just been kind of sitting around. But we finally have acquired the resources we need to get this going again. And so you can make super lightweight, super strong metal alloys, and I think that that's just awesome. If you have any questions, leave a comment. We'll watch them, we'll respond to them, and we'll answer them. Don't forget to like and subscribe.